Okay, so again, sorry for the interruption in between. There was some network issues, but now we are back with the presentation. So thank you for joining us across the globe. So good evening, good afternoon, and good morning to all the participants who joined us across the globe. In the next session, during the next 30 minutes, we will take you through the motivation, how we incorporate fuzzing for improving quality along with security, and then share our experiences of deploying coverage-guided fuzzing. So let me start with some motivation. Now, according to the McKinsey Soft Coster, it shows that the automotive software complexity has grown fourfold in the past decade, whereas the productivity has increased only 0.5 times. Now, looking a bit deeper into what you mean by the complexity, Sheikh already touched upon this point. So we are talking about 150 million lines of code in a car today. And if you take the NASA error rate of 0.5 defect per 1,000 lines of code, which is very low, you're talking about 1,500 errors that is possibly there in the cars today. And let's look a bit more concrete into a Volvo 220 vehicle software. The source code contains 10 million conditional statements and 3 million functions, which are invoked in 30 million places in the source code. So this is going to explode. The complexity will explode in the next decade. And parameter we can gain advantage is to increase the productivity and efficiency. Now, bringing a different dimension about how connected the cars are, we are seeing a shipment of 70 million connected cars by 2026. And we also need to consider that we have increased connectivity interfaces. So we have the Wi-Fi, cellular, Bluetooth, which is common in lots of cars today, but we're also talking about ultra-wideband, NFC, and DSRC. And this is resulting in increased attack surfaces. So with this, you well understand the motivation of why we need to focus on quality along with cybersecurity. We see fuzzing beyond cybersecurity. We see fuzzing for quality assurance. Now, let me start with a very simple example. First, we have the specification. And then the developer implements the system based on the specification. Andreas touched upon the topic that even the experts these days cannot develop software that is defect-free, which is very true. And these developers who are experienced, mainly because of the increase in complexity, we see that though they have implemented functionality, which is the intended behavior according to specification, it is also observed that they fail to implement certain functionality or they implement incorrect functionality, which is leading to side effect behavior. Now, the tester finds these bugs during testing using both positive testing and negative testing. Now, the challenge is if the developer is done an implementation a bit different, and because of the vast amount of invalid input for the negative testing, it could be the case that the tester will also fail to detect the defects. And this can be largely covered by fuzzing. And the high level of automation, including high defect and vulnerability detection capabilities, makes fuzzing a good choice for effective and efficient testing. Now, let's look into some of the reasons why we have poor quality. So we have no common understanding of requirements. And the clarity reduces from customer, and it gets worse when it reaches the tester. And there is a different level of understanding when the requirements flow from the customer. You break it down, and then when it actually completes the phase of requirement engineering and until we get into the testing, where we are focusing on test-driven development, we are seeing that the understanding of requirements are very different. And the other factor is that we have lesser time for development than before. The complexity is increased, the scope is increasing, and earlier, some of our products, we were talking about a project duration of 3 years from the start of development to start of production. And today, we see the same products with increased scope and complexity. We have a reduced time of 1 year. And this is going to be difficult going forward because we are going to have more software and we're going to have faster time to market and the need for faster time to market. And we are also talking about software updates in the road. So we will have lesser time for the complex scope we have, and we need to also go for incremental development. We also well seen the fact that we have increased software complexity, and it is also observed that we have low test efficiency and effectiveness. Now, let's see what we can do to improve the quality. Few of you would have already heard about the shift left paradigm. And this ensures that we have early error detection and prevention because we incorporate testing in an early phase. We can look into how we can increase the test effectiveness because we have a wide space of negative testing, which we saw in the previous slide. And now we need to find effective testing that can cover also the unexpected corner cases. We need to look into how we can increase the test coverage. And of course, we all know manual testing is time consuming, so we need to find ways to do test automation and increase the test automation in our systems. Fuzzing can be a game changer, yeah, with the high level of automation and increased test effectiveness and increased code coverage. Therefore, we decided to incorporate fuzzing in process reference models way earlier. So you can see the process reference model, which also includes the cybersecurity engineering process groups. And to start very early stage of software development, we have fuzzing included as a part of software unit verification, software integration test, system integration test, and of course, as a part of the security process for risk treatment, verification, and validation. We will not limit you to the V model here because we are talking about software development, incorporating Agile, and we can also see that this is applicable in the Agile development as well. In the next slides, René will explain to you a bit more deeper dive into how we deployed coverage-guided fuzzing and what are the challenges we faced. Over to you, René.
Okay, perfect. Thank you very much. Can you see my screen? Yes, this seems to work. Okay, perfect. So let me continue. Now, in this next part, I would like to share some of our lessons learned while trying to apply coverage-guided fuzzing. And I'd like to start with the challenges which we are facing. Now, First off, typically in automotive, we have very large technical diversity when it comes to microcontroller architectures. This is illustrated on the right side. There you can see an overview over the architecture distribution across some of our business units. And this technical diversity typically makes the application of existing tools for fuzzing somewhat challenging, because those tools typically focus on x86 and Linux as a platform. This is not something which is as widespread in automotive. And one result of this is that typically you will either need to port your source code. Then this again involves more or less effort. This is pretty much based on your specific project. Or you can choose to use emulation, but this is unfortunately not always that easy or not always an option. Again, it depends on your project. Now, the second issue which we face, this was also mentioned before, are the numerous hardware dependencies. So with coverage-guided fuzzing, as you know, we're testing on a software-only level. So that means we need to abstract those hardware dependencies. But this in effect also means that you need to remodel the hardware behavior with a sufficient precision. And again, this incurs additional overheads. Another challenge are software dependencies. Software development in automotive is typically a very distributed thing. Again, this is depicted in an overview on the right side. This is an AutoSAR Classic implementation, and their components, which are marked in different colors, can all come from different parties. And one result of this is that also tool and build chains are becoming much more complex. And if you want to use coverage-guided fuzzing, in many situations, you want to basically integrate those tools directly into the build chain. You need to do so very early, but this can then become rather challenging. Now, a related challenge here lies in the decision on which level you actually want to start testing, because you have multiple options, as we also will see in the next part then of the presentation. One approach would be to basically focus on single modules, test them in isolation, but this again makes the issue of software dependencies much more prevalent. A complementary approach would be to try to test the overall software system. But now, this typically then means that you also somehow need to take care of the hardware interfaces. And in this case, that means that you, again, have a large additional overhead because you somehow need to simulate or emulate the hardware. And if you should choose simulation, then this means that you need to be able to compile the full software stack in a way that allows you to start with fuzzing. Another typical characteristic of automotive software is the statefulness. So that basically means that individual parts of your overall system typically very much depend on the state of the rest of the system. You typically need to provide a specific sequence of inputs in order to reach specific states. And only if you do so, then you actually can create runtime behavior where a bug might manifest itself, or to just basically get consistent behavior or high coverage. And now reaching those specific states with fuzzing sometimes can prove challenging again, and again, you need fine tuning. And finally, this also sometimes makes it harder to just reproduce findings, because it's not always clear if a certain state, which is required to trigger a bug, could also be reached in the real system. And also the fact that you need to stop dependencies and that you need to simulate your hardware makes this more challenging. So usually it's not that feasible to remodel everything with a precision of 100%. Okay. Now, I believe all of those challenges are quite typical when you start testing automotive software. And this being said, what were our experiences when we tried to overcome them? As many projects do, we started our first attempts with coverage-guided fuzzing on a unit test level. And now some interesting insights here. So for some tests, most of the bugs which we actually found were within the test code itself. And only a minor part was found in the actual functional code. I believe that should not be too surprising if you think about it, because who tests the test code that much? Yeah. And while, of course, finding then bugs in there also helps to improve the test code, the immediate benefit is rather limited because this impedes the overall testing progress. The reason behind this is that for many fuzz testing approaches, in order to effectively continue, you typically should directly fix any bugs that you find. Because otherwise, the fuzz testing process will rediscover the same bug again and again. However, if you always directly need also to fix the bugs in the test code, then this will take away time from the resources you have for testing the functional code. The second, and I believe very early and basic insight, is that just introducing sanitizers, such as address sanitizer, for example, really proves to be very helpful. Yeah? So as soon as we did this, we already started finding additional bugs, and we hadn't even started fuzzing yet. We just recompiled our unit tests with some sanitizer support. We ran them again, and we found bugs which we had not seen before. So lesson learned here is, because the overhead is not that much, start using sanitizers if you can. Really, it's a quick win. The next interesting points are requirements in terms of coverage. So coverage guided fuzzing here can be really helpful, obviously, because it increases the coverage per definition. Traditionally, often unit tests are used in order to reach a certain level of coverage. But I believe in most cases, unit tests should actually focus on functional aspects, not so much on negative testing. And now in this situation, fuzzing really helped us to rather easily reduce the required effort in order to reach high test coverage. However, of course, it's always important to keep in mind what kind of assurance you get from specific coverage results or types, because yeah, having 100% test coverage really does not mean that you will be bug-free, of course. All right. So now, after those experiences with integrating fuzzing into unit tests, we also started to go more into a direction of module level testing. And here we selected some single high priority modules and started fuzzing them in isolation. So what did we learn here? For some findings, developers soon argued that the generated inputs by the fuzzer could actually never take the same values in the real system. And the data in this case was usually provided by another component, by some dependency, or for example, the RTE. And it was deemed trustworthy because there were well-defined specs regarding potential outputs. And this basically led to the discussion. And I mean, of course, you always can argue in direction of secure coding, defense in depth. But I believe here this is also only half the truth, because we also need to think about well-defined trust boundaries, even within our overall software systems, because this in the end will really help you to understand where and what to test in the best way. Yeah? So just going for all public functions of a module might not always make sense, at least not if you have really reliable constraints to the data that will be processed. And another lesson learned was that module dependencies for us can be really tricky. Remember, our goal was to test modules or a number of modules in isolation. And this now implies that we have the outgoing dependencies, which somehow need to take care of. And for this purpose, we decided to follow a very easy approach, provide fuzz data, not only from the top, so meaning to the dependencies to other modules, but also from the bottom for the hardware dependencies. And basically, the idea was to fuzz the module from all sides. After all, it should be robust and even be able to handle situations where hardware might provide invalid data. We managed to address this by just connecting the fuzzing engines to the stubs and then get the data from them. This, however, also proved to be challenging due to the overhead for stub generation. I guess it's not surprising to learn that doing this manually does not scale at all. After some time, however, we managed to automate this process to a certain degree, which made the approach much more feasible. But still, the generation part needed to be done iteratively again and again, because we had regular changes in our inter-module dependencies due to ongoing development. And another lesson learned here was that sometimes we would get findings that just did not make sense. And after additional investigation, we found out actually those were somehow false positives. And this is something that you should not have that much with fuzzing, right? Now, the reason behind this was that basically we just had outdated documentation, because the stubs which were generated were based on this documentation. And for some functions, after, for example, the function signature had been changed, the documentation did not correctly reflect this yet. And as a result, the stubs were faulty. And we found stuff that if the function had been called correctly, would not really happen in the real world. However, this, of course, also shows something else. First, fuzzing can even help you find bad documentation, but as a consequence of this, you can also prevent later integration issues. All right. Now, after those experiences with module level testing, we decided to go even a step further and now try fuzzing on a software system level. And this approach definitely has the most overhead. So effectively, what we did was we implemented a simulation, and that simulation now needed to be sufficiently close to the real system to again not produce any false positive findings. This meant additional overhead to fine-tune the system over time so that it works as it should. This could be supported by several actions, by of course comparing the simulation to the real thing. And what we, for example, did, we took some test cases that described intended behavior and made sure that those test cases also work on the simulated system. But still, to a certain degree, the confidence for any produced findings can sometimes be rather low. And then in this situation, what you might want to do is basically check for, it depends on the nature of the identified bug, if this bug then can also be reproduced against the real system, because basically if you do this on a software system level, the inputs should easily be also reused for the real hardware. However, software system level testing, of course, also has some major advantages. This is why we started doing this. And this is first, we got rid of those inter-module dependency issues. We're testing over a system which is already fully integrated. Second, I believe that was the most important point. Implicitly, we also tested the integration between all modules as well. And now please recall this point about stub generation and bad documentation. In many situations, bugs, and also specifically security bugs, typically appear at an interface level. So when different parties start integrating stuff, but they have subtly different understandings of how the interfaces are specifically meant. And this is, of course, sometimes hard to test, but in this scenario, then this test is inherently included into the testing process, and as a result also leads to more meaningful results. So far, this has been the approach which we have chosen and right now are also using on several projects. Now, regarding those overheads, of course, for all new projects, we typically still have those additional onboarding efforts to get everything up and running and for the fine tuning. But what we noticed is over time and with platform reuse, this overhead really becomes much more manageable. And of course, at the same time, you also always need to prioritize a bit to get the most out of your efforts. Okay, so let's summarize. Based on our experiences, fuzzing, specifically coverage-guided fuzzing as well, has huge potential even beyond cybersecurity. If you use it early enough, you might not even need to check for a specific bug if it has security implications or not. You just fix it and then you're good. At the same time, we have learned that specifically for automotive software, it can be really hard to apply, and that definitely does not exist one size fits all approach yet, unfortunately. But if you manage to overcome those challenges, this is a really nice approach. And the interesting thing is that over time with refinement and automation, it also becomes more and more effective. Now, when you think about fuzzing as a testing technique, I think it's quite clear that it is an immensely valuable addition to other techniques which exist as well. But at the same time, it does not really stand for itself. And what we need is we need to think about how to integrate fuzzing with those other testing techniques, because some of those are here to stay. They cannot just be replaced. And in the end, you want to have a holistic approach that basically helps you create the best results for a given amount of effort that you can invest. And of course, this is not just about the technical integration, but it's also about integration into verification and validation processes. Yeah, because I believe this is basically just the essential part in order to get everything together then.